Okay, welcome back everyone. So we have been discussing in this particular class this important derivative called the Lagrangian derivative, right? So there is a couple of things that I just want to quickly wrap up, and then we'll move back to the flow visualization that we were discussing, right? So Lagrangian derivative that you just saw. So Lagrangian derivative in cylindrical and spherical coordinates. Yeah. So for cylindrical coordinates, for example, the overall equations remain straight. It's very simple and something that you are probably already familiar with. So okay, the first term is obviously the partial derivative with respect to time, and then the second is ur del r, and then the next one will be u theta. Okay, wait a second, u theta, but there's a 1 by r term now, and del theta plus uz del z. Okay, what about the spherical coordinate system? The spherical coordinates is going to be again something very similar. So you will have ddt of whatever quantity you are taking. The first one is the partial derivative, obviously. The second term is also again very similar. The third term is identical to the cylindrical coordinate system, and then finally it's the last term that changes a bit. So this is now sine theta phi, right? You've probably done this before for some other problems. Okay, so and in just vector form, if you want to write this, then it's rather straightforward again. Right, so this is your acceleration now, right? So the acceleration is now given by this term. Okay, great. So we can move back to the topic of the flow visualization that we were discussing, and I hope you like the video that I had shown you. It's just a part of a much larger video by the National Science Foundation. Actually, there are many in that particular series, and if you have free time, you can always watch some of them. They're pretty good. And the reason I wanted to show you the video is because sometimes the concept of streak lines and path lines, so in fluid mechanics there are these three lines that are very important: streamlines, streak lines and path lines. And the concept of path lines seems often more intuitive, but when it comes to streamlines or streak lines, it becomes a little bit difficult to imagine them. Streamlines you might have already been familiar with, so you might not find that much of a difficulty. The streak line sometimes is a little bit difficult to imagine, but in that video I hope it was very clearly and visible what those streak lines mean. Okay, so first maybe we'll deal with the streamline. So the definition of a streamline is actually rather straightforward, and a streamline is a line such that it is tangent to the velocity field everywhere. Okay, so if I were to draw a line and say that this is a streamline, so let's say this is the streamline, then by definition the velocity at a given point is coincident with the tangent of the curve. So at every location the streamline is tangent, or the tangent to the curve, the streamline is coincident with the velocity field vectors, which means that there is no point on this curve where there is a normal direction of the velocity, right? So the implication of this is basically there is no flow across a streamline. And streamlines can also be experimentally visualized, but it's not all that straightforward. In fact, you have to reconstruct it from the velocity information. So you have to know how to do that, right? So let's say you have this curve. So at a given location, let's say this curve is given by y equal to fx. Yeah. So the tangent to this line at any location is my dy by dx. But my tangent is coincident with the velocity field vectors. So which means that if I were to take this is ux and uy, so these are the components of the velocity. So this is the velocity field vector. So this slope would also be given by uy by uz. Okay. So this is actually then equal to uy by ux. So this portion is basically the slope of the velocity vector, whereas this part is the slope of the streamline. And they have to be equal to each other. Okay. So this is for a two-dimensional flow. If the flow were three-dimensional, if flow were 3D, then you would have flow in the xy, so in xz and yz plane, you still have this relationship and dz by dy equal to uz by uy, which means, so in a more generalized case, you have these three different equations, right? If you combine all these equations, so if you combine this equation right here, this equation and this particular equation for a 3D flow, so we'll just clarify that for a 3D flow we get dx by ux equal to dy by uy and dz by uz. So this becomes the important equation and this is equation for a streamline. Nice. And because of the particular case, because of the way we have defined streamlines, there will be no flow across a streamline, right? In fact, you can create slightly more complicated geometrical how should I put it? Well, you can create what is known as a stream tube, right? So by combining many streamlines, one can create a stream tube, and a stream tube may look like something like this. So if you have many such lines, and you can create this kind of a tube such that there is no flow across a stream tube wall. So all the flow here remains inside, okay, and basically the surface of this stream tube is composed of all these different streamlines. And you can also make what is known as a stream filament if you just shrink this down more. So this was rather straightforward. So this is quite interesting that this becomes the governing equation for the streamline. So which means that if you know this velocity field, then you can reconstruct the streamline from there. Okay, good. That was interesting. Now for streak line, and you saw it in the video, so it will be easy for you to reconcile the definition. And the definition here then would be that a streak line is a line such that, okay, so ST stands for such that it connects all fluid particles that have passed through the same point. Remember the video showing the hydrogen generation and how that was forming a line. So basically there is a line where all the hydrogen bubbles have passed basically at the tip of the needle at some time, right? So they have passed through the same point in space at a previous or later time. So basically, again, remember the video that we saw. So we have let's say a needle, okay, or a dye injector, and all these dyes are going to form a line. Okay, so this is dye molecules or hydrogen bubbles, but they need not be this or any particle that faithfully follows local velocity, local fluid velocity. So how do you know whether a particle can follow the local fluid velocity? Well, there is actually a number called the Stokes number. Okay, so we will not go into it right now. Maybe later we might encounter it. Stokes number tells you whether a particle is following local velocity well. Okay. But if we assume that the fluid velocity, the particles are such, the dye molecules or the hydrogen bubbles or whatever the particles are such that they have the appropriate Stokes number and that they do follow the local fluid velocity, then all of these different points have passed through this initial location at some point of the time or the other. So there was some point at which these particles were here, and if they were here, they are following this local velocity, right? And if they were following local velocity, then how do we figure out what the equation of motion is? Well, this means that if I take, now see, here I am talking about dye molecules or hydrogen bubbles or particles, which means I can follow these particles. So I need not take, I can simply take my normal total derivative, time derivative, for x, where x is is related to this streak line, right? So this x is always equal to u, because wherever it is following the local velocity, such that, okay, so by the way, okay, so maybe I'll just quickly write that u bar, this is the local velocity field, and this is x here relates to the position of the particle itself, and this particular equation such that x bar at t equal to t naught was equal to some given x naught. Okay, and here this t naught is not the initial time. Okay, this is some t naught, this is not necessarily the initial time right here. So this is some t naught, so this is variable. Okay, so it's important to remember that this is a variable quantity. In fact, it is the parameter. So if you solve this differential equation subject to this particular condition, you will end up with solutions that consist of a set of parametric equations in t naught. Okay, good. So this helps us solve what a streak line is. And then we have the third and the final category, which is called the path line. And a path line is more simple to understand. It's very intuitive, because in the path line your particles are following, it's basically you're following the trajectory of a particle. That's rather straightforward. So basically a path line is the trace of a line, the trace of a particular particle is the trace of a particular particle as it moves from one point to another. So it is the actual path that the particle takes. Okay. So experimentally, how do you see this? It can be done by visualizing a particular tagged fluid particle and taking maybe a long exposure photograph of the fluid motion. So if you have access to a path line, basically these are snapshots. So at some time t naught, the particle was here. At some other time t, the particle is somewhere here, but it basically goes through this. This is now the trace of the particle itself. Obviously, you have to, this particle is the fluid particle. So experimentally, if you are doing this tagging, whatever is the tag, that again has to follow my previous condition, that it should faithfully follow the local fluid velocity. Okay, and that is the trick. That is the important number, the important rule that you must remember in order to figure out what the equation is for this. So the equation for path line is rather straightforward. Once again, the time derivative. So this is basically the Eulerian perspective. Sorry, the Lagrangian perspective. You're following a particle again, right? Just like the streamline case. So this condition remains true, that given a particular velocity field, the local velocity must always match the particle velocity, right? So u is the velocity field that has been given to you, and x is the location of the particle itself. But this condition, this equation has to be subject to the condition such that x at t equal to t naught equal to x naught. But now this t naught is a fixed value. So this t naught is no longer a variable. So this t naught is a fixed value. Unlike this particular case where it was a variable quantity, this now is a fixed value. So now your variable actually is the time t itself, right? So if you solve this particular equation subject to this condition, you will get a set of parametric equations in time. Okay, so that's the simple difference between path line and streamline. Okay, great. So we have seen these three important lines, and all these three lines in general are not the same. Okay, so note, in general, path lines, streak lines, and streamlines are not identical. Obviously, if they were identical, what was the point of doing all this hard work and trying to define this particular situation, right? And only in case of a steady flow they are identical. So for steady flow, they are identical. Okay, and I want you guys to do this as a self homework problem. Please try to show that for a steady case these are identical. So the first question you must ask yourself is, how do you define steady flow? Remember that in steady flow it was the partial derivative of the velocity field, or the Eulerian velocity field, that we take as 0, right? Good. So we have come up with these, we have understood these three different lines. Okay, now okay, maybe what I'll do is I'll give you a problem to solve and you can work on that. Okay. And maybe I'll solve only part of the problem here. So let's say a velocity field is given by this is, let's say there's a two-dimensional velocity field and the two-dimensional velocity field is known to you. Okay, and in this particular case it is minus v naught y x square plus y square by half I hat plus velocity x square plus y square to the power half again, and this is j hat. Okay, so a two-dimensional velocity field is given to you. So u is a two-dimensional velocity field and the flow velocity is not uniform. So the flow velocity is changing with spatial location, and the question is, what is the streamline, streak line and path line for this particular case. Okay, so for this particular case, if you the slope of the streamline, okay, so I'll just give you maybe a minute to start working ahead of me, and okay, so can you do that right now? It's just a good good practice to work on these problems right away. That way the equations will just sort of get set in your head. Okay, I've given you some time, so I'll start working on it, but don't you can keep working on it separately. Okay, so for a streamline, we know, sorry, so we can do this. We have this integral which is actually the solution. You can now, if you want, you can put limits. So let's say if the streamline does pass through a given point x naught and y naught, then and x and y are the variable points, then you basically will get so I hope you can immediately recognize the streamlines are circles. streamlines are concentric circles in this case. Okay. Since the flow is steady, we already know, I've already asked you to do this as a self homework problem. Since the flow is steady, the streamlines and path lines are identical, but I'd again encourage you to verify that on your own by solving the other equations. Just that's just good practice. Okay, good. Okay, so I think we have understood a very important issue about flow visualization. And the next part that we have to start looking at is something called the Reynolds transport theorem. Okay. Okay. And we had looked at the one-dimensional Leibniz theorem, and in that case that was a slightly simplified version of the Leibniz theorem. And right now I'll give you the multivariable example of the 1D Leibniz theorem. So the 1D Leibniz theorem says that if you have the ddt of, and this is in the book itself, I think. This is similar to what we have seen before when I was doing looking at some of the mathematical preliminaries, but the only difference being this f now here is a function of two variables. Okay, so there I just consider the single variable example, but if you have a multivariable problem, actually two variables to be more specific, then this equation looks something like this. Okay. And this Leibniz theorem also has a three-dimensional equivalent of it, and in the three-dimensional equivalent, what people do now is that you have to do this integration over a volume. Okay, I'm not going to do this right now, but I'm just going to write the left hand side, and I'll ask you. Okay, so I'll just quickly write down what I'm trying to do is the three-dimensional equivalent of it. So this is a generalization of the Leibniz theorem. So if you have d dt, and on this side now you have, again you have this term, but now this is a, now this has now become a vector, right, dv, and this integral now has to be carried out over a volume. Okay, so this is over some volume. The volume itself might be a function of time. Okay, just like here the limits are a function of time itself. So the limits a and t, they are also changing. I have missed okay, I have missed something here. This is dx, wait a second, that's okay, so this is dx equal to, right, I think the rest of it is fine. Yeah, the rest of it is good. Yeah, so in that I had missed the, so this is the one-dimensional Leibniz theorem, and this is the three-dimensional one. Okay, so this So what I'm now going to do, and I'm going to complete this part in the next class, and the reason I'm leaving it here is because I want you to sort of think, how do you do this generalization of the 1D Leibniz theorem. If you want, you can also read it up, so that might be a good idea, just to get yourself a little bit familiarized with it. You should be able to find this generalization rather fairly easily on the net, okay, if you want to take a look at it. Okay, great. So I will stop here right now, and we'll pick up on the Leibniz theorem in the next class, and then we will proceed on to learning about the Reynolds transport theorem from there. Okay.